Hello, my name is Professor Dr. Virginia Toy, and I'm here in the Cascade River Valley in southwestland in New Zealand. I'm standing in front of an outcrop that I'd like to describe and explain to you. So we're actually in the mouth of a small creek that drains off the orange hills in the background, which are the Dun Mountain Ultramafic Belt, and the rocks in this creek are particularly orange due to the high iron content and the oxidation of that iron, i.e. the rusting. The creek here drains from a lake called Theta, and in front of us we see a vertical face. This vertical face actually has been uplifted during Alpine Fault earthquakes, so the recent trace of the Alpine Fault runs pretty much parallel to the base of this slope. You can see that the outcrop comprises at its base a series of gravels that are old stream gravels. Overlying that there are some fine layers. Those layers are glacial varves, silty layers that are deposited in the lakes that would be at the front of a glacier in the last glacial maximum, which ranged back to around 17,000 years ago. And overlying those there is also another gravel layer which is bearing the orange ultramafic boulders that you see in the river at my feet. We've studied the glacial varves here. They're particularly interesting for two reasons. Firstly, you'll notice that the layers off on the right hand side are sloping down towards the right. That reflects the fact that the layers up there, up the top, when an earthquake happens, there's uplift of this side of the fault and the layers then just collapse down into the stream. The second thing that's interesting is that within that sequence, particularly just one layer just above the top of the gravel and another two layers further up, the glacial varves are deformed into folds that are shaped like this. They go up and down and up and down like this, and they all have a very uniform fold axis and an asymmetric shape to them. Those folds were generated by what is known as seashing. That's the kind of sloshing backwards and forwards of the glacial lake that occurs when earthquake shaking occurs. And these layers would have been at the sediment-water interface in that lake at the time the seashing occurred. So they were all uniformly sheared, and the whole fold axis would be perpendicular to the seashing direction, so the shaking would have been perpendicular to that. That seashing occurs, during an earthquake, and we can actually determine from the physical properties of the sediment, we can get an estimate of the actual shear stress that has to be applied through the seashing, through the sloshing of the water. So that gives us an estimate of the peak ground acceleration. That's the horizontal acceleration that's associated with that earthquake. Within this layered sequence there are also pollens, and the pollens, we were able to sample the pollens and date them, and also estimate each of the varve layers is an annual layering, so one forms every year. And we were able to work out that this sequence and other sequences in the Cascade Valley here, the folded layers are distributed around every 300 years apart. And this means that we have a paleo earthquake record in this region from around 17,000 years ago, or a little bit less, that demonstrates a recurrence on the Alpine Fault for earthquakes of the order of 300 years, which is really similar to the recurrence interval at the modern day. That means that in this region we basically have one of the longest paleo earthquake records on the planet, which is pretty astonishing, really quite amazing. I've been down here looking for bedrock exposures, trying to analyse the clay mineralogy of the principal slip zone of the Alpine Fault with two field assistants, Michael Offman and Fox Meyer. And we are now waiting for a helicopter to collect us and take us back up to Jackson Bay.